All right, this is not my favorite video right now. Take 65,000. I'm losing my mind in here. All right, here we go. Let's get this done. There's a beam traveling through. We see that it happens to be at a 43-degree angle right here. That's going to become important in a minute. Right now, notice these dotted black lines. Okay, that's just supposed to indicate the original direction of the beam. I'm going to take a rectangular slab and I'm going to slap it on here, and we see all kinds of stuff going on. I'll briefly explain that and then get on with our lives. Okay, at this first surface, here's the normal. Notice the angle is 43 degrees to the normal. There's a reflection off the front surface. Then this light comes through. This is approximately about 25 degrees here. And then notice there's a reflection off the back surface. Some of that gets refracted out. And then there's the output beam on the back side of the slab. Notice the input beam is originally right this direction, and the output beam is parallel to that. As you can see, it's parallel to this dotted black line. We say it has been displaced by this small amount. Measuring that, it is somewhere between 1.5 and 2 centimeters. I don't know if that ruler shows up on the screen. There is some thickness of the laser beam. There's some thickness of this line. That is probably good to within a couple of millimeters. Let's say it's 1.75 plus or minus 2 millimeters. Obviously, this is going to be complicated. If this is slightly angled, this might be a little bit different, but whatever. All right, so we're doing these numbers that I just told you. And I'm going to turn on the lights, go to the main board, and get this frickin' problem over and out of my life. I'm so tired of this problem. Oh my goodness, I've been so many takes. For some reason, this one, I just keep screwing up something on the board every time. Let's not do that this time. Okay, going to the main board. Minimizing this. So yeah, if you hadn't guessed, this is a tricky problem. It's easy to screw something up, and you'll see what I mean. All right, now in this case, here are the dimensions. It's a 10 centimeter tall slab, 6 centimeter wide slab. I think those are pretty good. We had an experimental angle of 43 degrees input. Experimentally, we found this was about 1.75 plus or minus 2 millimeters. So basically somewhere between 1.5 and 2 centimeters. Looked pretty good. We're assuming the index outside is 1, the index inside is n. Instead of calling this theta 1, I'm going to call this theta, just because that's what I did in the workbook problem 33.37 on page 14. All right. Now, what is this? I don't need that. Okay, so in this case, you can see this is the original direction of the beam here. This is the original direction of the beam. And then we see it was refracted through and it came out. And our goal is to derive an algebraic result for D in terms of the index of the slab, the input angle, and the thickness of the slab. Now, if you want to pause the video and try and do this, I encourage you to do that. Pause the video now. 3, 2, 1. Okay, almost certainly most of you are like, what is going on? I have no clue. So I'm going to give you a hint and see if that helps. With these problems, it often helps to consider these two, right? Draw triangles, do geometry. I'm going to give you a hint here. This triangle is useful, or at least that's what I used. And this triangle is also useful. And this is the one that people don't usually see. All right. Now you know why that blue line was there. And I was like, whatever, I've so many takes. I'm going to pause again, give you a second to try. If that gives you the clue you need, see if that works. All right. See if you can do the math. I'm going to pause. Here we go. 3, 2, 1. I'm coming back at you. I'm going to draw these two triangles over here. I like to try and draw them in approximately the same orientation so I get less confused. Something like that. And I'm going to give this length a name. I'm going to call it L. We saw that this length here is D. And then down here, I see there's another triangle. my attempt to draw that. This isn't very good. It's a little better. Just doing the best I can here. This angle was theta 2. This side is T. And this length is L. And if I'm going to try and figure out D, right, let's see if I could do that. I know what T is. In theory, if I know these indices and theta, I could, in theory, figure out, let's see, I'd have T and theta. In theory, I should be able to figure out L and figure out L. But how do I get from L to D? I'm going to need some kind of angle. Can you figure out what that, an angle, figure out one of the angles in that triangle? If you want to pause the video, give it a shot. 3, 2, 1, here I go. This is the trick. Now you know I had that line there. This big angle here is theta and theta. So what's left for this little angle inside? That is going to be theta minus theta 2. That's the move. All right, so in this case, this angle right here is theta minus theta 2. Now pause the video and see if you can do the whole problem. Remember, you got the solutions. I'm going to proceed in 3, 2, 1. All right, hopefully I don't screw this up. Let's see, this is a right triangle right here. I can figure out T and L are related here. Let's see, cosine. T over L. And this is the spot that I screwed up before. Notice that L should equal, move this up, move that down. It should be T over cosine theta 2. Who cares about the color coding there? Let me make sure that's right. L comes up, cosine goes down. So now I can go to this triangle and I see, let's see, SOHCAHTOA opposite. So sine theta minus theta 2 should equal opposite D over L, which now I should be able to, let's see, I know this value of L. So let's see, I believe we can, okay, our goal is to solve for D. Let's do that. D should equal L sine and now you could take this and plug it in there. Over. I'm going to take a second to write this on the other board. If you want to pause the video at any time, go for it. Let me see here. It was T over, and I'll move the board in just a second. Just making sure. T over that times this. Okay, I'm switching the board now. And I'm going to this board right here. Come on. All right. Jeez. Okay, getting an error message on my screen. I sure hope this is recording because I just can't do this again. All right, so now, remember, we're trying to eliminate theta 2. We're trying to get this entire thing in terms of theta, t, and the other variable n. So I'm going to remind ourselves that n air sine theta was equal to n in the plastic sine theta 2. If you don't remember where that comes from, let me go back here. Right, that's Snell's law at this interface. N air sine theta should equal n2, which is n sine theta 2. So let's go back. Come on. Come on. Oh, whoops, I'm on the wrong button. There we go. And now in this case, we could simplify this. This is 1, and that just cleans things up a little bit. So notice sine theta 2 is equal to, let's see, n over, whoops, 1 over n sine theta. Now, one thing that you could do is you could take sine inverse and plug it in. But that's going to get a little bit ugly, it turns out. Technically, that would fit the bill, but man, that's a very difficult formula to work with. I'm going to do another thing here. And I'm trying to figure out what cosine of theta 2 is, and you'll see why in a minute. So 1 minus sine squared theta 2 equals 1 minus 1 over n squared sine squared theta. Well, isn't that cosine theta 2? If I take the square root of both sides, that's a convenient way to get rid of theta 2 in this term without having the inverse sine functions in your answer. And we can also use a trig identity on this term. A trig identity on this term says sine theta cosine theta 2, sine theta cosine theta 2 minus, it's going to be sine theta 2 cosine theta. And I'm going to make sure I didn't screw up the trig identity really quick. Sine A minus B is sine A cosine B minus cosine A sine B. Yes, this is it. Okay, so if you plug all that stuff in, maybe I'll do 1 or 2 more lines here just to help you out. I'm plugging in the trig identity for this. Right? And now what we could do is we can shift some stuff around here. D is equal to, I'm just going to keep T, this is the term with the right units, and then I'll have sine theta. So that term actually ends up being kind of nice. That's pretty simple. T sine theta. And then we're going to have minus sine theta 2 cosine theta all over cosine theta 2. Now, if we plug in this information, what was sine theta 2? It gives us this 1 over n thing here. And then down here, we get this big square root thing. And I'm going to actually factor out this 1 over n, right? So if I factor out a 1 over n, that would give me n squared minus sine squared. And I think you'll see why in just a minute. And when you put all that in there, let's see if that ends up being, did I screw something up? Let me see. Trying to see where we get that. Oh, I got you. I see. Let's see. I should be able to now factor out a sine theta. Okay. So in the end, I think what you'll see is you get this result here. And so even though it takes a lot of work, this ends up being a little bit easier than having inverse trig functions. to be honest, if you ended up using the inverse trig functions, I'd probably give you the points on the test because you would have fulfilled the requirement. But I do think it's kind of nice to see some of the moves that I've just shown you. That helps you kind of, it's nice to have final answers that this is a lot prettier than having really long, ugly inverse trig functions inside of trig functions. That's a sign that there's a clever thing you can do. It's worth looking around for it. So there you go. And notice the result. This ends up matching up using these things. We assume we have about 2 sig figs here. This matches up pretty well with the result we had, which was 1.75 or so, plus or minus 2 millimeters. All right, we're looking good. Finally done with that video.